Hey, how you guys doing today? This is Colin, also known as CYIT on YouTube, and today we'll be doing a PCB design. This is a Robert Feranec PCB design, an ESP32 to be exact, designed by Espresso Systems. I want to say it's popular because it has integrated Wi-Fi and Bluetooth connectivity. Now, if we just get started, I do plan on doing my own PCB designs very, very soon. But as of now, this is really working for me. I must say it's working. So really, this is not even going to be an outline of the PCB design. This is really going to be an explanation for our schematic capture. Now, this schematic capture, if we look over here on our screen, is I want to say, I think you can say maybe like open source. It's well documented for sure, this ESP32 schematic. And this is where we get our schematic from. So ESP32 dev kit. And if we take a closer look, this is our power supply here, or our linear regulator. We have all of these things, our connectors, the buttons that we'll be using. So everything is open source, everything is well documented. And we'll just go ahead and give it an explanation. Make it easy to understand. I know a lot of the times we'll do a tutorial and it'll say, hey, I want you to do this, I want you to do this, and I want you to do this next. And they leave no room for why. Like, why are we doing this? What does this mean? So it's like, are you really learning if you don't know why, or if you don't ask those questions? A lot of these videos, even my videos, you got to put in extra work once the screen goes off. You got to go ahead and do your own research to figure out, fill in those gaps and figure out what you don't know. And I think that's why these videos of other people's content is so helpful, and that's why I do them, because they're so good to learn from. They kind of give you like the blueprint or the outline, and you learn from them, and then you can go ahead and further that knowledge on your own. But as stated earlier, I will begin my own PCB designs, because I think that's the next step in the learning process. So take a look at our schematic. Like I said earlier, designed by Robert Feranec on YouTube. I think that's how you say his name. It was extremely helpful, I must say. So first, let's take a look at his design. This isn't his design. This is his design the way I did it. His was, I'm sure, a lot better. He's been doing this for a very long time. This is an easy EDA. Easy EDA. Easy EDA is cool. It's pretty cool. I must say, I did my first PCB design in KiCad, and I like KiCad better. I definitely enjoyed KiCad as compared to Easy EDA, but I mean, if you don't have a lot of space on your laptop, maybe you will like the fact that this is what I like about Easy EDA. My laptop storage is almost full. I need to go ahead and get me like a hard drive or an SSD so I can store some of this data. But not only is it good for that because you can store it online, you can actually save your account. Maybe I don't know what I'm doing, but on KiCad, I don't know how to make an account. So I hadn't had a chance to save my account. I just got to log into that same on this computer to get all of my information. I could be wrong though. Maybe I'm gonna have to just delete this out of the video. But we'll just have to go ahead and see about that. So I showed you guys the PCB design. Now let's go ahead and get started. We're going to talk about these four first, and then I'll point them out on our PCB layout, and that'll allow you to visualize a little bit better. So if we jump right into it, we have power input selection. Let me go ahead and zoom in for you. And our power input selection is really just a header, and this header has 3 pins. And on our pin 1, we have 5E_V bus, and everyone knows that V bus comes from our USB connector, which we're not quite there yet though. So just give me a second. Pin 2 is our output, and this output is to our linear. Let's go ahead and put that on mute. Nice. So pin 2 is our output, and this output is to our linear regulator to the right of me. I don't know if it's your left. And then on the left of our pin 2, we have 5V external EXT, which is a 5 volts coming from an external power source connected. It'll be connected to our connector. So it'll come in from our connector to this header. So the way this header works is we want to short 2 pins, right? So our pin 2 is our output to our linear regulator, and our linear regulator is going to give us our main power rail that's going to provide power to our whole microcontroller. So if we short our pins 1 and our pins 2 together, we'll have our power coming from our 5VB bus, which is our USB connector, and it'll connect to our 5-volt output, which goes to our linear regulator, and that's how we'll power our microcontroller. And if we have our pins 3 and our pins 2 connected, we'll have an external 5-volt power source that'll come in and connect and then go to our linear regulator that way. Our power input selection just allows us to prioritize one power source over another based on what's more convenient for us, based on requirements, based on availability. And nice. So I did mention my linear regulator a few times while I was talking about my power input selection. And this linear regulator is 5 volts to 3.3 volts, which makes a lot of sense because our linear regulator will go ahead and take a higher input voltage, a higher variable input voltage, I think you can say, and go ahead and give you a consistent and stable regulated output voltage. In this case, 3.3 volts. All right, so we'll get 5V, and then we'll get 3.3 volts out. Now, if we look at our linear regulator, this one has 1, 2, 3, 4 pins. On our input, which is our pin 3 V in, and on our output, which is our V out, pin 2, we have decoupling capacitors connected to ground. And what these decoupling capacitors do is they attenuate high frequency noise. And the way they do that is they act kind of like a short. So capacitors allow high frequency noise to pass through the ground, and that noise is going to take the easiest route. And that's what it is. Not only will it attenuate high frequency noise, but those capacitors will also absorb energy and output that energy whenever we need it, so that we have a stable power delivery, you know. That way we don't have any variations in our power supply. Nice. So if we slide over a little bit to our right, I don't know if that's you guys' left, we have our power LED, and our power LED is connected to 3.3 volts. Keep in mind our 3.3 volts comes from out of our linear regulator, right? And what does that mean? It means that whenever we have 3.3 volts coming from our linear regulator, our power LED will be on. Our power LED is connected to a resistor, a current limiting resistor, 1K ohm. That way it doesn't burn up, and it's also connected to ground. So this ground is completing the circuit. So whenever we have 3.3 volts, the circuit is completed and our LED is powered on. Now our power LED is a little bit different from our user LED in the fact that our power LED is completed with ground and our user LED is connected to a GPIO pin from a microcontroller. In this case, IO18. But we do have a few similarities. 3.3 volts, same deal. A resistor, this one is 560 ohms, so it's a little bit smaller, but it's still a current limiting resistor. And then here we have an LED as well. And our user LED is also known as an indicator LED. It's like a feedback LED. I think this is the LED that you go ahead and you blink. Like whenever you see those videos and it says like blinking LED on your Arduino, this is probably the LED that you're going to be blinking. It's our user LED. Now, as stated earlier, this LED is just a bit different. It's connected to IO18, our GPIO pin. And this is what allows us to blink our LED. This is what allows us to control our LED. As you know, our GPIO pins can either be high or low, in a high or low state. When our IO18 GPIO pin is in a high state, there's no potential difference from our 3.3 volts and our IO18. You know, so our IO18 may be 3.3 volts and our 3.3 volt may be coming from our power supply, and therefore current isn't flowing. But when our IO18 is pulled low by our microcontroller, which we can control through our microcontroller firmware, and I'm sure you guys have probably seen that too, we can go ahead and complete the circuit because IO18 is low, and it'll allow current to flow through. So you may post IO18 on, off, high, low, and the circuit will be completed, not completed, completed, not completed, ground or 3.3, ground or 3.3. And that's what will cause our LED to blink on and off and on and off. That's how you get that the blinking effect. So I did say I wanted to show you guys exactly what I was, or allow you to visualize. I know a lot of the times, see, the schematic can be a lot different from the PCB layout. Like it says, hey, this has to be connected here, but it doesn't tell you exactly how it has to be connected. Let me give you an example. So if we zoom in a bit, I apologize for that. This is our header here. This is our header. As you can see, we have 5V bus, and our 5V bus, if we slide over a little bit, is connected to our USB connector. Now here, what we have is a polygon, this red area, or maybe you could say like a power plane, and that just allows our current to flow better because there's a lower voltage drop. So we have better power delivery, which is very important because this 5 volts, it goes into our power, our linear regulator, and that linear regulator provides power for the whole board. Not only do we have 5V bus here, we also have 5V EXT or external here, as stated earlier, coming from a connector. And that connector could be connected to like an external power source. And then, I also stated if you put like a jumper here between V bus and 5 volts or external and 5 volts, you can power it from those two different power sources. Now, as you can see, we have that 5 volts coming into our linear regulator, and this is that input capacitor, that input decoupling capacitor here. So if we take a look at our schematic, it was just kind of like a line. And that line is showing like, hey, these are connected. But you wouldn't have thought, if you don't do PCB design like I don't, this is only my second video, it's connected with the power plane. Like it just has to be connected, but it's not necessarily specifying how. So that's why I'm kind of going over this. I think this will be really, really helpful. So this is our input pin here on our linear regulator. And then this is our ground pin here. And then here are pins 2 and 4. And these are, pins 2 is our output, but we connected pin 2 and pin 4. Now we also spoke about our power LED. And this is our current limited resistor here that we see on our schematic, and that current limit power goes through our current limited resistor to our LED. So whenever we have power output from our linear regulator at 3.3 volts, the circuit is always completed, and we'll go ahead and we'll have our LED power, our power LED power on. Now if we scroll down just a bit, we have our user LED indicated by user here. We have another resistor, which is also connected to 3.3 volts, and power will go ahead and flow through here, or current, I guess you can say. And this is very similar to our power LED as stated earlier, but instead we have this via here, and this via connects our user LED to our GPIO pin, our IO18 here, and our IO18 is connected to, if we slide over, to this pin on our microcontroller. So by controlling the firmware on our microcontroller, we can control if our IO18 is high or low, which means we can control if our user LED is either on or off. So next we have our USB connector. And our USB connector, or our USB, stands for Universal Serial Bus. And our Universal Serial Bus can be used for power distribution to our PCB, in this case 5 volts. But not only that, it can be used for communication. Now that communication is done here through our USB-D plus and our USB-D minus differential signals. And our differential signals, these two right here on pins 2 and 3, D minus and D plus, are a pair of conductors with equal and opposite signals. And what that means is, as one, say our USB-D plus, as the amplitude on our USB-D plus signal increases, the amplitude on our USB-D minus signal decreases at the same amount. So when USB-D plus increases, USB-D minus decreases at the same amount. Now this is really helpful because this can reduce EMI, electromagnetic interference. It can mitigate or attenuate high frequency noise, and this leads to more reliable data transmission across longer distances. So the way we represent zeros and one, because at the end of the day, this is binary information that we're transmitting. The data is binary. So what happens is, When the amplitude, okay, so as the amplitude of D plus increases, the amplitude of D negative decreases. And if the gap between our D plus and our D minus signal is larger, this will be seen as a 1. And if the gap between our D plus and our D minus signal is smaller, it'll be seen as a 0. So this is how we can transfer ones and zeros through our USB D positive and USB D negative lines. Now I guess I missed C3, 100 nanofarad capacitor, and this is just a decoupling capacitor. So as stated earlier, this helps attenuate high frequency noise by sending it to ground, because this capacitor will kind of act like a short. It won't be a short circuit, but it'll act as a short circuit. And not only that, it'll store voltage, and then it'll release power when needed, when it realizes voltage fluctuations in our VCC, or our output from our USB connector. Now we slide over literally just a little bit. We have 1, 2, 3 ESD protection diodes, or electrostatic discharge protection diodes, I guess you can say. And we have these due to something called the triboelectric effect. And basically what it states is that when certain materials come in contact with each other and then they separate, our USB connector can become electrically charged. So it can gain electrons, and maybe our cord can like lose electrons or something like that. So basically our USB connector will become electrically charged, and we'll have a buildup of electrons on this USB connector. And what happens is our ESD protection diodes allow this static electricity to go to ground. That way we don't interfere with our data transmission. So that's why we have those ESD protection diodes right there. Now, if we scroll down just a bit, we'll go ahead and we'll have two transistors. I want to say the Errata said NMOS transistors. And we'll have a few other things. The capacitor, we have an GPIO pin here, resistor, and a header. Now, why do we have this, and what exactly is an Errata? So a Errata document is provided by a semiconductor manufacturer, and it details a known issue or a known problem with a particular device. Here we are. This is the USB Express family CP2102N Errata. So our CP2102N is going to be our USB to serial bridge, or UART, or USB to UART bridge. But we went ahead and we added this information here on our USB connector, which is okay. So let's go ahead and take a look at our issue, figure out how we can solve it, and let's just do it that way. So look, if we take a look here, detail Errata descriptions, description of Errata. So during and immediately following power on reset, the USB D plus and USB D minus pins are undefined. That's not good. So these pins can be either logic high, logic low, or mid supply. And this behavior typically lasts for about 15 milliseconds. And then D minus and D plus, the USB D minus and D plus pins can then operate normally. However, some USB host devices, say a computer, may require USB D plus and D minus pins to be in a known state during or immediately following power on reset to operate properly or to start properly, right? So now we have a workaround. Adding an external circuit to the USB D plus and D minus pins can force the desired state on these pins during and immediately following power on reset. So if we take a look here, we have exactly what was stated in our CP2102N Errata, USB D minus and USB D plus. We have our they can be undefined for 15 milliseconds, I want to say, when our device cuts on. And that's not, we want it to be in a known state when our device first powers on. So what we went ahead and did, or what the Errata instructed us to do, is go ahead and add two transistors. And I didn't read the other part, but it did say connect a GPIO pin. So that's what we have. We have our two transistors. We have a GPIO pin. Here we have a capacitor to attenuate high frequency noise. And then we also have a pull down resistor. So let me explain how this works. So we have two transistors, and on the gate of those transistors, we have this resistor. And this is, I want to say, a pull down resistor. So basically when nothing is on like this signal here, or on these two gates, it's naturally pulled down the ground. Now here we have IO23, and we have a resistor here to connect these two signals. And IO23 can either be high or low, because it is a GPIO pin, which can be controlled by our microcontroller. So When IO23 is high, what happens is we have a high signal here on our gate and high here on our gate. And this will allow our USB D minus and D plus pins to go to ground. So they will be in a known state during power on if we program our IO23 pin to do that, and they'll be low. So that's the known state right there. So that solves our problem. However, I know Robert had us go ahead and add a header here. And what this header allows us to do is when we short our header following power on reset, what will happen is we'll have 3.3 volts come through here, and it'll go onto the gates of our transistors, and it'll pull our USB D minus and our USB D plus lines low, which means that we can manually go ahead and do that as opposed to having to configure our GPIO pin and in code. So here we are. This is our USB to serial section, and this is our USB to UART controller, I guess you can say. And this is going to be our CP2102N. So what our CP2102N does, it's in the name. It allows devices that use UART communications, say our microcontroller, to communicate with devices that use or through a USB port, or that use USB, or that communicate through USB. So say our computer or any other devices. So what it does is it translates USB data format to UART compatible data formats and vice versa, because this allows for communication back and forth. Now, what I want to do is I want to talk about connections, because I know for me and schematics, the biggest thing is why. And I think what I'm doing with this, I wouldn't even call it a series, but just with these videos, is I'm asking the question why. Because I think that when you ask the question why, it allows you to really understand it. Like, I really want to be able to look at a schematic or even look at a board, which will probably be difficult, and say, hey, I have an idea, or I think that this may do this or this may do that. And this is why this board isn't acting how it should be acting. Like, I can diagnose a board by looking at it, or I could look at a schematic and say, hey, this is supposed to do this, and this is supposed to do this, and here's why. You know, so that's what I'm really trying to get closer to. Right. So let's go ahead and talk about connections, and maybe just maybe this still contradicts it. That kind of contradicts itself. But if we take a look here, we have our CP2102N data sheet. And if we scroll down to page 6, this CP2102N data sheet will answer a few questions. All right. So right here on page 6, typical connections diagram, CP2102 data sheet. So the figure below shows a typical connection diagram for the power pins of the CP2102N devices when the internal 5 volt to 3.3 volt regulator is not used. So in our case, we're not using the internal 5 volt to 3.3 volt regulator because we have our own external linear regulator that I spoke about earlier in the video. So if we take a look here, we have our RSTB signal connected to VIO, which in our case is 3.3 volts through a 1 ohm resistor. We also have ground connected to 2 decoupling capacitors, which attenuate high frequency noise and store energy or store power to release it when needed. And this is also connected to 3.3 volts to 3.3 volts. In our case, it'll be, or 3 volts to 3.6 volts. In our case, it'll be 3.3. And when we don't have the internal 5 with a 3.3 volt regulator connected, we'll go ahead and connect our VDD, but we'll also connect our VREG in signal to this same line as well. So if we look here, we have RTSB, 1 k ohm resistor, 3.3 volts, 2 decoupling capacitors to attenuate the high frequency noise and provide power when we need it, so that we have stable power delivery. We have VDD here on pin 6, and then on pin 7, we have our VREG in connected. So I know I said that I would like to know why. And in this case, the why is because the data sheet says so. But hopefully at some point, I can be the person making the data sheets. Or I can figure, okay, so why? Because the data sheet says so. Why does the data sheet say so? And I think that that's kind of what I want to figure out. So we keep going. Here we have so we keep going on page 9. The figure shows a typical connection self-power diagram for the USB pins. Okay, cool. Including ESD protection. So we had our ESD protection diodes, but we had these on our USB connector here, right? So that makes a lot of sense. Now this is going to, because I know my next question was, why do we have this voltage divider? So we're going to take a step back for a second. What exactly is a voltage divider? So a voltage divider is two resistors, and they're connected in series, which means there's only one path from power to ground, and it divides our voltage up. Like it divides our voltage, it ratios our voltage. Now, there's a few things that I didn't know about resistors before I did this Robert Feranec video. Like I knew what voltage dividers were. I knew, but I didn't necessarily know how they worked. And I found out something interesting. So basically voltage dividers voltage dividers are like ratios. And what that means is here we have a 221K ohm resistor, and here we have a 47.5 K ohm resistor, and 5 volts is coming in here. So let's do the calculation really quickly so we can figure out what that is. So number one, let's scroll up. Here is our voltage divider formula. So V out, so this is what we'll get here. So V out is here, and V out is connected to our V bus on our CP2102 in. So V out is here. And V out equals R2, R2 being R12 in this case, our second resistor in series, 47.5 K ohms. Divided by R1 plus R2. So R1 is the top resistor, multiplied by Vn. In our case, Vn is 5 volts. So that is that's going to be how we can calculate the voltage on V out. So let's go ahead and scroll down. And we have R2 divided by R1 plus R2. So in our case, R1, the resistance is 21.2K, R2 is 47.5K, and the input is 5 volts. So with that being said, if we do 47.5 divided by 22.1 plus 47.5 multiplied by 5, we'll get 3.4 volts. Now, what I didn't know is that if we change the resistor to 2.21 ohms, so we erase the K and we put the decimal here. If we had 2.21 ohms and if we erase the K here and we put that here and we have 4.75 ohms and we put in 5 volts, the output would still be 3.4 volts. So I didn't know, and maybe you guys don't care, but I didn't know that this was based off a ratio. I thought I didn't know that, and I just find that so cool. So let's scroll up. So why don't we? My question then was, how come we don't just go ahead and we don't use a 2.1 K ohm, a 2.1 ohm resistor and a 4.7 ohm resistor? Why do we use 22.1 to 47.5? So although, and I'm just reading right now, though it's often the ratio of the resistance values that determines the output voltage, whenever you create a voltage divider, you have to be aware of overall power consumption of the circuit. So I'm under the impression that resistors go ahead and they release heat basically when they divide voltages and they step down voltage. So if the resistance isn't high enough, it'll release so much heat it'll burn up. So next we can talk about V-bus. And we scroll the page now on our CP2102 data sheet, 2102N data sheet. We see that we have a 22.1 K ohm resistor and we have a 47.5 K ohm resistor connected to our V-bus signal. And I was curious as to why, I stated earlier. So there are 2 restrictions on the V-bus pin voltage. The first is absolute maximum voltage. So this is the most voltage you can have on that pin, and it is 5.8. So how do we calculate this? It was VIO. In our case, VIO is 3.3 volts plus 2.5 volts, and it'll be 5.8, and that is shown here. So the first is absolute maximum on the V-bus pin, which is defined as VIO plus 2.5, so 5.8. which that wouldn't even be a problem anyway, but I'm assuming that the USB connector could be higher than 5 volts. So I'm assuming that there are so many other applications for the CP2102N, not just in microcontrollers, possibly. So, or maybe in microcontrollers, but maybe those microcontrollers are higher powered. They have a higher power USB input. And maybe that's why we have this voltage divider here, because we may not always be working with 5 volts. So the second is the input high voltage, VIH, for VBus to detect when the device is connected. So basically, if our is 3.3 and it's minus 0.6, so if we're not getting at least 2.7 volts on our VBus signal when VBus is plugged in, then our CP102N won't even detect that that we have something plugged in and we're trying to communicate. So here's serial signal handling, and it doesn't really seem like a lot, but let's just go ahead and jump right into it. So here we see RxD and we see TXD, and RxD and TXD are our receiver and our transmitter signals for our UART communication protocol, and our RxD and TXD will come from our USB-to-UART controller, I guess you can say. And one thing that I didn't know, and honestly, this should be something that's like pretty simple, I guess, but I didn't, because this is like I said, I haven't really done a bunch of these, and this was my first time seeing an RxD signal or a receiver signal connected to a transmitter signal. And like I said, this should be common sense, but well, number one, for some more background information, our TXD0 and our RxD0 are also for our UART communication protocol, transmit and receive, send, I guess you could say, and input and output, I guess you could say. And these are going to be connected to our ESP32 module. But obviously we want our RxD and our TXD to be connected, because we want our transmit to the transmit of one device or the output of one device to go to the receive or the input of another device, and vice versa. So that's why we have TXD and we have RxD connected. Now I was also confused about what exactly were these resistors for. And like I said, this could also be common knowledge, but these resistors are just used as jumpers. As you see, there's 0 ohm resistors. So there's no voltage drop. There probably is a voltage drop, but I'm just going to say there is no voltage drop because it says there's 0 ohms. And this is just using like a jumper or a bridge to connect these two signals, which I didn't know at first. So now we go down just a little bit. We have this circuit here, and this circuit is an auto programming circuit. So basically, what it's supposed to do is it's supposed to allow us to update or change the firmware on our microcontroller without having to manually put our microcontroller into program mode. This is supposed to do that for us. Now, if we take a look here, this is our enable signal, and our enable signal is pretty straightforward, pretty simple. Even I knew what an enable signal was. When our enable signal is high, our microcontroller is on, and when our enable signal is low, our microcontroller it resets. So we come over here a little bit, we have a reset button, and when our enable signal is high, our microcontroller is on. So obviously we want to pull up resistor because we don't want our microcontroller to inadvertently reset. So let's have a pull-up resistor here. Let's make sure it's high, it's in a known state, and unless we want that microcontroller to reset, it won't. Now, how do we get that microcontroller to reset? Well, we have it connected to a button here. And when we press our button, or it's labeled SW1, maybe for like switch, but when we press our button, it connects to ground, and this 3.3 volts for this pull-up resistor can go to ground, and our enable signal will be low, and our microcontroller will reset. Now here we also have a decoupling capacitor, and this is going to attenuate high frequency noise from our 3.3 volt input. Now we're going to come back over here, and we also have IO0_BTN. So I want to say that IO0_BTN. Well, number one, IO0 is a GPIO pin from our microcontroller, and this GPIO pin specifically is a strapping pin. So for strapping pins, or on a strapping pin, the value, whether it be 0 or 1, can be read by software, and it'll perform a specific task. That software, I guess you could say, will perform a specific task based off if the value on our GPIO strapping pin is either a 0 or a 1. So in our case, our GPIO pin is determines our boot mode. So number one, our GPIO pin or our IO0 pin has a internal pull-up resistor. And when the IO0 pin is high, it's going to be SPI boot mode. And SPI boot mode basically is a boot mode where we use SPI communication protocol, and we go ahead and we get our initial operating system, or maybe our initial firmware from flash memory. So I want to say that this is firmware or information or data that we had previously used. It was previously uploaded. It won't be anything new, and that's what happens when our GPIO pin is high. Now, when our GPIO pin is low, our GPIO 0 pin is low, we'll go ahead and we'll enter download boot mode. So download boot mode allows us to update the operating system or update the firmware stored in flash memory through a UART, maybe like a USB connector or something like that. So we can go ahead, we can write new firmware to our microcontroller, and that'll allow it to perform different tasks. So when it's high, internal pull-up resistor, SPI boot mode, we'll continue our regularly scheduled programming. And when it's low, it'll be in download boot mode. We can go ahead and program our microcontroller. And then if we look here over at our user/boot button, we don't have a pull-up resistor, like I said, because that strapping pin, that GPIO 0 pin, has an internal pull-up resistor. Therefore, we don't, well, this capacitor is not fitted anyway. And when we go ahead and we press our button, this is how we will manually, well, it will be a combination between our reset button and our user boot button, but this is how we will go ahead and put our microcontroller into boot mode. When we press that SW2 or that button, we press it down, we connect it to ground, and that causes it'll be download mode. So it'll be low. Now, when we take a look at our ESP32 module, it's not really much to talk about. We obviously have all of these GPIO pins. We talked about a few of them during the video or earlier in the video. As stated earlier, we have our TXD0 and our RXD0 connectors. This is for our UART communication protocol. This is our power to our microcontroller, 3V3 here. And this is our enable signal, which we spoke about. And then we have our decoupling capacitors here. You guys know what those are by now. Now here we have, so this is our IO0, our strapping pin. Now this is the input/output from our button. So we spoke about that, but we also have another one on our connector. And this connector allows us to do the same thing. So basically this is it'll be like we'll get an input from our connector. If that connector pin is high, it'll be SPI boot mode. If that connector pin is low, it'll be download boot mode. So it serves the same purpose. We can just get that information from two different places, kind of like our header for the power selection part, I guess you can say. So lastly, we have our GPIO connectors, and these allow our microcontroller to interface with the outside world. So it can receive inputs, and it can also generate outputs on our GPIO, on our connectors.